Thanks for watching this video. I'm Yue from UT Austin. I will give you an introduction of the hyperbolic polynomial from theoretical computer science perspective, more specifically from the aspects of concentration, anti-concentration, and the discrepancy theory. It's a joint work with Zhao Zong from Adobe Research. So hyperbolic polynomial forms a very important family of polynomials in mathematics, which was first studied by Gardner in the theory of partial differential equations, and then it has been extensively studied in many areas of mathematics. Moreover, hyperbolic polynomial has many theoretical computer science applications. For example, it serves as a hyperbolic polynomial has many theoretical computer science applications. For example, it serves as a key component in proving the famous Cartesian singular problem, and also in constructing bipartite Ramanujan graphs. Also, hyperbolic programming in optimization theory is the generalization of linear programming and semi-definite programming. And Gervis found that hyperbolic polynomial is important in approximating the permanent, which is an important problem in sampling and counting. Moreover, recently, it is discovered that the spectrohedral representation of some particular hyperbolic polynomial is related to the algebraic complexity. Here is the definition of hyperbolic polynomial. Let hx be an unvariate degree D homogeneous polynomial. We say hx is hyperbolic in direction E in Rn if he is non-zero, and also the univariate polynomial ht minus x, which is a polynomial in variable t, has only real roots for any x in Rn. Let's look at some examples. The first example is hx equals to the product of x1 to xn. It's easy to see that it is hyperbolic in the whole positive orthon. In other words, in any direction E in Rn such that all coordinates of E is positive. The second example is called the Lorentz polynomial, which is hx equals to x1 square minus x2 square minus to the xn square. This is a very useful polynomial in physics, especially in the relativity theory, because it describes the light cone in Minkowski space. This polynomial is also hyperbolic in the direction E equal to the first standard basis vector 1, 0, 0, 0. This is because when we consider the univariate polynomial ht minus x, it has two real roots, x1 plus or minus square root of x2 squares plus to x3 squared plus xn squared. Another example is when hx equals to the determinant polynomial, in particular, the determinant of symmetric real matrices. This polynomial is hyperbolic in the direction when we vectorize the identity matrix. This is because since X is a symmetric real matrix, it has only real eigenvalues, and the univariate polynomial ht minus x equals to the determinant of t times I minus x, which is the characteristic polynomial of x, and its roots are just the real eigenvalues of the matrix X. Let's talk about the hyperbolicity from a geometric view. To consider the three-variable Lorentz polynomial hxyz equals to z squared minus x squared minus y squared, we can draw the surface of hxyz equals to 0, which is the light cones in 3 dimensions. Recall that the hyperbolic condition is ht minus x has only real roots. In this picture, the right line corresponding to the line t minus p for any p in R3, and E equals to the third basis vector 0, 0, 1. As we moving the line for different p, we can see that it always has 2 intersection points with the surface. Since h is a degree 2 polynomial, we know that ht minus p has only real roots, and thus h is hyperbolic in the z direction. However, if we look at the x direction, that is, if we set E prime equals to 1, 0, 0, this polynomial is no longer hyperbolic in this direction. This is because when we move in the line, as in the right picture. Sometimes it has two intersections, but sometimes it has no intersection. Therefore, ht minus p doesn't always have real root, and it is not hyperbolic in the x direction. So motivated by the example of the determinant polynomial hx equal to the determinant of a symmetric matrix X, where the roots of determinant ti minus x are the eigenvalues of the matrix X, we can also define a more general notion of hyperbolic eigenvalues for any vector in Rn. So let hx be a degree d hyperbolic polynomial in direction E. Then for any x in Rn, we define its hyperbolic eigenvalue lambda hex be the d real roots of hte minus x. Without loss of generality, we may assume that lambda 1 is greater than lambda 2 is greater than lambda d. And for convenience, when it's clear from the context, we often omit the subscript h and e and just use lambda x to denote the hyperbolic eigenvalue of x. And similar to the spectral norm of a matrix, we define the hyperbolic spectral norm as the largest magnitude of the hyperbolic eigenvalue of x. For example, when hx being the product of x1 to xn, and we set E being the all-one vector, then the hyperbolic eigenvalue of a vector x is just x1 to xn in descending order, and its hyperbolic spectral norm is the infinity norm of the vector x. Here are some basic properties of hyperbolic eigenvalues. The first property is the linearity of the hyperbolic eigenvalues. More specifically, for any real number s and t, if we consider the hyperbolic eigenvalue lambda I of s times x plus t times e, then we know that it is equal to s times lambda I of x plus t if x is non-negative, and it's equal to s times lambda d minus I of x plus t if x is negative. This is because the hyperbolic eigenvalues lambda I are ordered from large to small. And the second property is the Newton's identity. Basically, it says that the univariate polynomial ht minus x can be expressed in terms of the sum of some symmetric elementary polynomial of the hyperbolic eigenvalue of x. And the third property is that the largest eigenvalue of x, lambda 1x, is a convex function in terms of x. So the main contribution of our paper is to extend the properties of matrix eigenvalue and matrix spectral norm to the hyperbolic setting in three aspects: concentration, anti-concentration, and discrepancy. More specifically, for concentration, we generalize the matrix channel form to the hyperbolic channel forms. And in anti-concentration, we extend the positive spectrohedral anti-concentration in a recent paper to the hyperbolic anti-concentration. And in discrepancy theory, we generalize the matrix Spencer conjecture to the hyperbolic Spencer conjecture. And we also generalize the famous Hallis singular theorem to the hyperbolic Hallis singular theorem. Let's get started from the channel form. So the study of concentration of sums of independent random variables has a long history, and channel form is one of the most popular and useful tools in TCS. Here is the particular form of channel form for independent Rademacher random variables. that is the random variable Ri equals to 1 or -1 with probability 1/2. Then we know that the sum of R1 to Rn greater than t is the probability is at most 2 times e to the t squared over 2n. And also there are many other different forms of channel bond for more general scalar random variables. We can also generalize the scalar version of channel bond to the matrix version. There is a long list of work on this topic. And here is a commonly used form of matrix channel bond for Rademacher matrix series. So let x1 to xn be d by d symmetric matrices, and let R1 to Rn be n-independent Rademacher random variables. Then we consider the spectral norm of the sum of Ri xi. The probability that the spectral norm is greater than t is at most 2d, d is the dimension of the matrix, times e to the minus t squared over 2 sigma squared, where sigma squared is defined as the spectral norm of the sum of xi squared. We generalize this theorem to the hyperbolic setting, that is, let hz being the m varied degree d hyperbolic polynomial in direction e, and let s and sigma be 2 parameters, and giving x1 to xn in Rm be n fixed vectors, such that each xi has at most s non-zero hyperbolic eigenvalues, that is, its hyperbolic rank is at most s, and also the sum of xi's hyperbolic spectral norm square is at most sigma square. Then for R1 to Rn being an independent Rademacher random variable, we can show that the probability that the hyperbolic spectral norm of the sum of Ri times xi is larger than t is at most 2 times e to the minus t squared over sigma squared times log of s plus 1. Let's consider some particular hyperbolic polynomials. First, if hz is just z, a univariate simplest hyperbolic polynomial, then we know that x hyperbolic norm is just the absolute value of x. And then theorem 1 just recover the Hofstein's inequality. And theorem 1 is optimal in this case. And the second example is when xz being the Lorentz polynomial, z1 squared minus z2 squared minus zm squared. In this case, if we set xi being 0 and concatenate with another vector vi for some vi in Rm minus 1, then we know that xi's hyperbolic spectral norm is just the 2 norm of the vector vi. And in this case, theorem 1 recovers the dimension-free version of vector value Bernstein inequality. And the third example is when hz equals to the determinant polynomial for some symmetric matrix. In this case, however, theorem 1 cannot fully recover the state-of-the-art matrix channel bond by trope for general xi. This is because our variance term sigma squared is larger than the spectral norm of sum of xi squared in general. However, for constant rank xi, these two quantities are of the same order, and in this case, our theorem is better than the matrix channel bond, since it does not have a leading dimension factor, as in the Chop's result. So for matrix channel bond, there is another useful form, which is for random positive semi-definite matrices, which are the matrix with only non-negative eigenvalues. In this case, we have this theorem that controls the minimum and the maximum eigenvalue of the sum of xi. Note that we do not assume any particular distribution of xi, so this is more general than the previous matrix channel bond. So can we also extend this theorem to the hyperbolic polynomial setting? The first thing to do is to generalize the concept of PSC to the hyperbolic setting. A natural correspondence is the so-called hyperbolic cone, which contains all the vector x such that all the hyperbolic eigenvalue of x is non-negative. we know that the hyperbolic cone is a closed convex cone. And equivalently, we can also define the hyperbolic cone as the closure of the connected component of the non-zero region of HZ that contains the hyperbolic direction E. And also, for any vector in the interior of the hyperbolic cone, H is also hyperbolic in that direction. And in particular, we can show that hyperbolic cone does not depend on particular hyperbolic direction. Now with these properties of the hyperbolic cone, we can prove this theorem, which is the hyperbolic Chernoff bound for random vectors in the hyperbolic cone. So if we consider x1 to xn being independent random vectors with support in the hyperbolic cone of hyperbolic polynomial hz, such that each random vector xi has hyperbolic spectral norm at most r for some parameter r. Now we define two parameters, mu min being the sum of the expected minimum hyperbolic eigenvalue of xi, and mu max being the sum of the expected maximum hyperbolic eigenvalue of xi. Then we can control the probability that the lambda d being smaller than mu min and lambda 1 of sum of xi is greater than mu max with some exponential tail. Now let's switch gear to the second aspect, anti-concentration, which is an important phenomenon in probability theory. So the famous Littlewood-Orford theorem proves that for uniformly random vector u in plus minus 1, the probability that u falls within the width2 boundary of a half space W x inner product at most theta is at most 1 over square root of n for any half space. Here the boundary means the W and x inner product is in the interval of theta minus 1 to theta plus 1. And it also has some consequence that the each coordinate of W should be at least 1. Recently, this Littlewood-Orford theorem has been generalized to the polytope AX at most B. And more recently, AY22 further generalized to the positive spectral hydra, which is the set of X such that the sum of Xi times some PSD matrix AI is spectrally dominated by another PSD matrix B. In our paper, we further generalize this anti-concentration phenomenon to the hyperbolic setting, which is the positive hyperbolic spectral hadron, which is a set of all vectors in Rn such that for some vector b minus sum of xi times ai for some ai in the hyperbolic cone is also contained in the hyperbolic cone. More specifically, we show that the probability that the largest hyperbolic eigenvalue of the sum of ui times ai minus b contained in any small interval minus delta to delta is at most O of delta. And last, let's consider the discrepancy, which is a problem about giving n subsets S1 to Sn of the universe n, and we color each element of n in red or blue, and we want to minimize the discrepancy, which is defined as the maximum over all subsets, such that the red element in Si minus the number of blue element in Si is minimized. By Chernoff bound and the union bound, it's easy to show that a random coloring has discrepancy at most square root of n times log of n. And in the celebrated result by Spencer, he proved that there exists a coloring with discrepancy at most 6 times square root of n. And it's natural to generalize this set discrepancy to the matrix discrepancy, which is shown in this famous matrix Spencer conjecture. More specifically, for symmetric matrices x1 to xn in Rd times d, such that each matrix has spectral norm at most 1, there exists a coloring R in plus minus 1 to the n, such that the spectral norm of sum of Ri times xi is at most square root of n. This conjecture remains open, however, there are some recent progress that proves some special case of the matrix Spencer conjecture. In our paper, we generalize the matrix Spencer conjecture to the hyperbolic Spencer conjecture. More specifically, we consider that giving any x1 to xn with hyperbolic spectral norm at most 1, there exists a coloring such that the hyperbolic norm of sum of Ri times xi is at most O of square root of n. Let me give you some remarks about this conjecture. If we set xz being the product of z1 to zm, then this conjecture corresponds to the set discrepancy problem, as is proved by Spencer's theorem. And if we set xz being the determinant polynomial, then this conjecture just corresponds to the matrix Spencer conjecture. And by our hyperbolic kernel form, we can prove this conjecture for any hyperbolic polynomial and vectors x1 to xn with constant hyperbolic rank. Another closely related problem is the famous Cartesian singular problem, which is proved by Marco Spellman and Srivastava in 2015. So giving you n vectors x1 to xn, such that the L2 norm of xi is at most epsilon for I in n. And more importantly, they are in the so-called isotropic position, which means the sum of xi times xi transpose being the identity matrix. Then for any k at least 2, there exists a partition of the set n in subsets S1 to Sk, such that the sum of vectors in Sj with xi times xi transpose has special norm at most 1 over square root of k plus square root of epsilon to the square for any subset. Actually, this Cartesian singular theorem implies a discrepancy bound for rank 1 isotropic matrices. And recently, it has been extended to the high rank isotropic matrices. And KLS further removed the isotropic condition of KS for rank 1 matrices and proved a stronger version of rank 1 matrix Spencer theorem. For hyperbolic version of Cartesian singular theorem, Random generalized the KS theorem, and in our paper, we further relax the isotropic condition to the sub-isotropic condition, as shown in this theorem. So let xz still be a hyperbolic polynomial in direction E, and let x1 to xn be n vectors in the hyperbolic cone, such that the sum of all hyperbolic eigenvalues of xi is at most epsilon for all vectors, and also the spectral norm of sum of xi is at most sigma for some parameter sigma. Then we can show that there exists an coloring R in plus minus 1 to the n, such that the hyperbolic spectral norm of the sum of Ri times xi is at most 2 times square root of epsilon times 2 sigma minus epsilon. Now let's quickly give you some main idea of proving the hyperbolic kernel form. There are 3 case steps. The first step is to reduce bounding the concentration probability to bounding the expected hyperbolic 2q norm, which is defined as the sum of all hyperbolic eigenvalue of x to the power of 2q. And then we use the deep result about hyperbolic polynomial, the Helton-Vinnikov theorem, which is proved a famous conjecture by Lex. More specifically, it says that for any 3-variable hyperbolic polynomial f, there exists a symmetric matrices A, B, and C in R d by d, such that this hyperbolic polynomial f x, y, z just equal to the determinant of x times a plus y times b plus z times c. This theorem does not hold for 4-variable hyperbolic polynomials. And Gurris proved a useful corollary such that for any n variable hyperbolic polynomial h, and for any 2 vector x and y in Rn, for any n, there exists 2 symmetric matrices A and B, such that the hyperbolic eigenvalues lambda sx plus ty for any st just equal to the matrix eigenvalue lambda s times a plus t times b. This corollary allows us to translate between hyperbolic and matrix. And by the conditional expectation, we can isolate each random variable Ri one by one and just consider the hyperbolic eigenvalue of Ri xi plus the sum of the remaining Rj times xj, which correspond to the 2 vectors x and y, and we can use the Gurris corollary and some matrix analysis techniques to bound the 2Q norm. Finally, let me give you some open questions. The first is, can we prove a tighter hyperbolic channel bond? Our results is not tight in terms of the variance, which recovers the original version of the matrix channel bond, and it has been improved by more recent work. Can we generalize these new techniques in improving matrix channel bond to improve our result? There is a barrier. That is, a key component in improving matrix channel bond is to use the matrix exponential e to the t times x, where x is a matrix. We can use the Taylor expansion to expand this exponential in terms of the sum of matrix polynomials. However, it seems very hard to define the powering operation of a matrix Xn in the hyperbolic setting. Another open question is, can we resolve the hyperbolic Spencer conjecture for some hyperbolic polynomials? There might be some hyperbolic polynomial where the hyperbolic Spencer conjecture is much easier than proving the matrix Spencer conjecture. On the other hand, it's also interesting to prove the equivalence of hyperbolic Spencer and matrix Spencer conjectures under the so-called generalized Lex conjecture, which says that for every hyperbolic polynomial, its hyperbolic cone is a spectrohedral set. The last open question is, can we find more applications of hyperbolic concentration or anti-concentration or discrepancy in TCS? For example, can we use our results to construct PRGs for the positive hyperbolic spectrohedral or even hyperbolic cone? Also, can we use our result to improve any hyperbolic programming solver? That's all. Thank you.